My name is Susanna Kohler. I'm the press officer of the AAS, and I am thrilled to welcome you to the penultimate press conference of the 243rd meeting of the AAS. We're in New Orleans, Louisiana. Today is Thursday, the 11th of January, and it is 10:15 a.m. And we're about to start the press conference, High Energy Universe. I am joined by my colleagues, Carrie Hensley, the Deputy Press Officer, and Ben Cassess, the AAS Media Fellow. They will be helping out running mics and taking questions from reporters online. And before we get started, I just want to remind everybody to check your cell phones, make sure they're not going to go off in the middle of the presentation. In terms of logistics, the previous press conferences have all had their briefing videos uploaded to the press kit online, as well as the press releases associated with them. And we've got about half of the slide decks also uploaded. So we'll keep working on that as they come in. But all of that is there for reference for you if you need it. And that can be accessed also from the press conference's Slack channel. It is pinned in there. So if you haven't joined that, please do, by all means. I encourage you to, and I encourage the speakers to join it as well. In case any reporters have questions for you, they can find you there. So I think we are good here. The way this is going to work, for those of you who have not attended a press conference before, is I'm going to give a brief introduction to the speakers and their topics here. Then they're going to go through and present one by one in order. And then we are going to move into a joint Q&A session for the whole group. So hold your questions until that Q&A session. If you're joining us online and you have questions, be sure to queue them up via the Q&A box in the Zoom webinar if you're watching via Zoom. If you're watching via YouTube, apologies, we don't have a way of interfacing with you, so you will just have to send your questions to the authors. And reminder that if you do queue up a question or if you ask a question in the room in the Q&A session at the end, to identify yourself and your affiliation and who the question is for before you ask the question. So today, as I said, we are talking about the high energy universe. We are going to first hear from Kimberly Weaver of NASA Goddard Space Flight Center on evidence of a Relic active galactic nucleus eruption. Then we will move to Pearlman from McGill University and Mohit Bhardwaj from Carnegie Mellon University, who will speak on unveiling the most promising formation channel of fast radio bursts using local universe bursts. Then Alexander Kashlinsky from NASA Goddard Space Flight Center will talk about evidence for large-scale anisotropy in the gamma-ray sky. And lastly, Michael Calzadilla from MIT will speak on how astronomers have found the spark of star birth across billions of years. So with that, I'm going to go ahead and turn it over to Kimberly. And do we see this on Zoom? Excellent. All right, all yours.
Thank you. So hello, my name is Kim Weaver, and thank you all for being here today. I'm trying to stand so that I can be seen and also project into the microphone. So I'm going to talk to you about how we used XMM Newton to find the relic of an eruption from an active galaxy. This is the first time this kind of signature has been seen in the light of hard, high-energy X-rays. Active galactic nuclei, or AGN, are bright cores in the centers of galaxies where supermassive black holes live. These black holes produce a lot of energy, and they can heat the surrounding gas and dust. Sometimes AGN power outflows, like powerful winds and high-speed jets, and these jets can travel far into intergalactic space. Here I'm showing a high-powered AGN called M87. The white colors in the middle are the galaxy, and you can see in the red colors the radio jets, and in the blue colors the X-ray jets. And this is what you might think of as a very strong, very luminous active galaxy. So why study AGN? One of the reasons that we study them is that we want to understand how AGN affect galaxy evolution. Their outflows and their jets can move material around inside the galaxy. And so you might think that there could be effects from that. We also want to understand how AGN can affect star formation in galaxies and whether we can trace prior episodes of nuclear activity across cosmic time to understand if there are evolutionary processes in place where AGN make a big contribution. So we can do this by using X-rays to trace not only the jets, like I showed in M87, but also the hot gas and the cold, dense gas created by the AGN outflows. And this talk discusses what we're seeing with cold, dense gas. So we used ESA's XMM Newton satellite to study the nearby spiral galaxy NGC 4945. Unlike M87, this is a low power AGN. And as you can see here, you don't see any jets. This is an optical image from the European Southern Observatory. So the other thing that's interesting about NGC 4945, it's in the middle of a starburst period. So it's also called a starburst galaxy. And what that means is that it's producing a lot of stars at a very high rate in a relatively short period of time. The other thing to note about this galaxy is that we're seeing it, it's a disk spiral, and we're seeing it almost edge on, inclined about 80 degrees with respect to us. And you can see here too, there are large dust lanes along the side. That's where some of this very dense molecular gas, this cold gas, lives that we are seeing in X-ray light. So on the right-hand side is an image, the image from our XMM observation. It's the same size roughly as the prior image. You can see that looks very different. So you have the optical galaxy with a disk. Now you're seeing a whole bunch of X-rays, and the red colors are the lower energy X-rays surrounding the galaxy in a large halo. But we're focusing on the higher energy X-rays nearer to the disk. But the great thing about XMM is it gives us high sensitivity and a very wide field of view. So in one observation, we can see the entire galaxy at one time. In the blue, I'll get back to it when it comes. So the blue here is the light from XMM's optical monitor. So that's also an optical image. So here we've zoomed into the center of the galaxy. The optical image is similar to the one before, but taken with XMM simultaneously. Transposed on top are the green contours of a large nebulosity of gas revealed by X-ray light in the light of what we call the iron K alpha fluorescence line. So this fluorescence occurs when high energy X-rays from the AGN interact with the cold dense gas, especially the cold dense gas along that dust lane, as you can see that it lines up. Now we've seen this signature before in AGN, but closer to the black hole, on the order of a few thousand light years across or less, and often less. But the cold gas in NGC 4945 extends for 32,000 light years along the plane and about 16,000 light years on its way into intergalactic space. That's an order of magnitude larger than we've ever detected before in the signature of the iron K alpha line. In the intensity map here, the brighter colors represent higher concentrations of X-rays. The yellow blob in the middle, that's the AGN. So we're seeing that AGN in the X-ray signature, but there are also point sources surrounding that. So the question is, what do we do about those point sources? Because they're getting in the way and we want to understand what we're seeing in the extended emission. So to confirm this extended emission, the next step that we took was to remove those point sources. We used Chandra observations, which Chandra has much better imaging resolution than XMM. So you can see all the point sources very well individually. And we removed those based on the intensity of those sources. So this image here is all the point sources and the extended emission. Then we took everything out but the AGN, and then we took the AGN out. So this is a final image with all the point sources that we could see and detect removed as best we could. So what's interesting is that it turns out, now we zoom back out, and the green contours are the same extended iron K alpha image that I showed before, overlaid on the optical image. So that's the XMM optical monitor again of the galaxy. The whiter contours are, the light gray are the radio polarization contours. The paper is not on here, but it's from Harnett et al. 1989. That's where I took those contours from. So that's radio light. If you overlay this radio polarization signature, you can see that these two peaks or blobs, if you will, kind of line up with the X-ray bubble on both sides. So top and bottom of the galaxy, we see the X-ray extent going up and down, and then you see the radio on both sides. Now, this radio emission indicates strong ordered magnetic fields, not like you see in a normal galaxy or even a starburst galaxy. And these authors suggest that this could indicate the presence of what might have been a collimated outflow, and it could have suggested an AGN ejection event a long time ago in the past. So the question is, what do we think is going on? What's happening? Well, this animation shows what we think happened. About 5 million years ago, the AGN erupted, and the jets that came out of that AGN slammed into the disk of the galaxy. They didn't go out perpendicular, they went straight into it, roughly at a 60-degree angle. So when the jet slammed in, they pushed that gas out and created this kind of wall maybe of dense molecular gas along both sides. Now, these jets, after about a few 100,000 years, theory predicts that if they're going to interact with that galaxy, they're going to be disrupted and disappear. So we don't see them now. But this was 500 million years ago, 5 million years ago that this happened. And the jets would be gone. But what we think is going on now is that we have left over in this illustration the Relic signature. So the Relic signature are these blue cloud-like features that are drawn here. That is this molecular gas compressed by those jets. So the jets at the center in this illustration, represented in the pink, indicate how the geometry worked and the angle of the original ejection event and the inclination of the disk with respect to us. So it's a very geometrical problem. The specific alignment is what lets us see this X-ray signature along the line of sight. Now, finally, what's even more interesting is the age of the starburst in this galaxy is about 5 million years. Our calculations from the dynamics of this event is that in order to get out to that distance, this event had to occur 5 million years ago. So the age of starburst, the ejection event, about the same. So we suggest that this event could have caused the starburst. The AGN erupts, starburst happens, and so this Relic signature could be crucial for understanding how this galaxy has evolved from an AGN phase to a starburst phase. And so we're understanding galaxy evolution by these data. And then finally, I'm going to take a drink of water here. So the next steps we can take are a couple of things. We want to look for X-ray polarization clearly to see if we see that because we see the radio polarization. And also the X-ray polarization can tell us a lot about geometry effects. So NASA's XB is clearly an opportunity to be able to do that. And then finally, we want to look at this object with CRISM to map that iron K alpha line out and get a good signal of maybe obtaining velocity structures to see if we're able to detect the outflow in NG 4945. So thank you. The iPoster abstract ID is listed here, and this paper is submitted to AppJ. It's currently in the revision process and hopefully will be published shortly. Thanks.
And I should mention that every speaker today has a press release coming out. So we'll add those to the press kit as well.
Good morning, everyone. My name is Dr. Aaron Pearlman. I'm a Banting postdoctoral fellow at McGill University and the Trache Space Institute at McGill. I'm here today with my colleague, Dr. Mohit Bhardwaj, who's a McWilliams Fellow at Carnegie Mellon University, to present results on behalf of the CHIME-FRB collaboration showing evidence of a dominant formation channel based on a sample of local universe FRBs. So fast radio bursts, or FRBs, are bright radio pulses which have durations of about 1 millisecond. The precise origins of FRBs remain unknown, but they originate from objects located far outside of our Milky Way galaxy. There's also now evidence that some fraction of the FRB population is produced by magnetars, which are neutron stars with extremely large magnetic fields. As FRBs travel through the cosmos, they propagate through intervening material. This causes the radio signal to become distorted due to dispersion, which causes the signal at higher observing frequencies to be detected before the signal at lower frequencies. And an example of this is shown on the right. Typically for FRBs, the amount of dispersion that you see is more than can be accounted for than from material from within our own galaxy. An important area of active research in the field involves identifying the possible formation channels of FRBs. There's evidence that some FRBs may originate from objects formed through prompt formation channels, such as magnetars produced from core collapse supernovae. However, there's also evidence that some FRBs may be formed through delayed channels, such as the nearby FRB found to reside in a globular cluster on the outskirts of the M81 galaxy. We use the CHIME radio telescope, which is located in Penticton, Canada, to search for FRBs in real time across the northern sky as part of the CHIME FRB project. CHIME FRB detects, on average, about 100 new FRBs per month. The CHIME FRB team is an international collaboration of about 80 scientists, which includes scientists, postdocs, and faculty from universities and research institutions in Canada, the United States, as well as other countries. We're here today to present new results on behalf of the CHIME FRB team. As the Earth rotates, CHIME FRB searches roughly a 220 square degree area of the sky for new FRBs. When an FRB is detected, we're often able to save the corresponding voltage data from each of CHIME's antennas. By combining the data from all of the antennas, we can obtain a better measurement of the FRB's position by forming tide array beams around where the FRB was detected and searching for where the FRB signal has the highest signal-to-noise ratio. This process allows us to obtain positions for FRBs that are accurate to about an arc minute, and in some cases, we can do better if the FRBs are very bright. The implementation of this capability was led by Dr. Daniele Micheli, who's also a postdoc on our team. This level of precision, importantly, allows us to identify the host galaxy of nearby FRBs. I'll now pass the podium to my colleague, Dr. Bhardwaj, who will tell you about the new results on behalf of the CHIME FRB team, and he also led this study. Thank you.
Now, using the software pipeline that my colleague Aaron described, we actually examined all FRBs that we published in our first CHIME FRB catalog. And using some predefined criteria, we found that there are 4 FRBs in our catalog for which we can actually able to pinpoint them to a host galaxy. And we found that all of those galaxies are in the local universe and they are spiral galaxies. Now, to really say something meaningful about the origin of FRBs or FRB population in general, we need to examine a larger sample. So what we did, we considered all FRBs in the local universe that were published in the literature, and we were able to, and we detected only, or we selected only those FRBs where the robust host associations were made. And I want to make a note of this, that over 50% of those local universe FRBs were discovered by our collaboration, the CHIME FRB telescope. And interestingly, we found all 18 local universe FRB hosts to be spiral. Now, this interesting observation we use to say something intriguing or important about the origin of the FRB, and to be precise, the most dominant channel to produce FRB sources. Now, inspired by the discovery of the FRB 2020-0120E, to a globular cluster in fact, this is the closest FRB localized to the M81, Messier 81 galaxy. The first question we ask is, can these sources be the dominant channel to produce FRBs? Now, if that is the case, then we anticipate only 28% of our host galaxies to be spiral. And that is because this fraction basically aligns with the distribution of mass in different galaxy types in the local universe. And we know most of the mass is actually in early type galaxies like elliptical. So using this observation, we can clearly rule out the possibility of globular clusters to be the dominant channel to produce FRBs. So it's likely that the M81 FRB is potentially an outlier. Now, the next question that you can ask is where these FRBs can lie. Now, if not globular clusters, a promising avenue is they are present within the disk of their host galaxies. Now, in that context, there are various models in literature that propose different ways to form the FRB sources. And in one hypothesis, it was suggested that FRBs are basically originated from the aftermath of supernovae that was caused by extremely massive stars that are located in dwarf galaxies that we call superluminous supernovae and long GRBs. And it is also potentially possible that most of the FRBs are not that exotic. They are actually produced by stars that we see in our own galaxy Milky Way, massive stars that we see that explodes as core collapse supernovae. Or else, it is also possible that these are not exactly young progenitor in the sense that they're not produced by the explosion of these massive stars, but they are produced by the remnants of these explosions, white dwarfs and neutron stars, and somehow they dynamically energize themselves to produce FRBs. Now, in this study, one thing we can clearly say that GRBs or gamma ray burst and superluminous supernovae cannot basically account the all-sky rate or occurrence rate of FRBs that we see. These are like at least a few orders of magnitude lower. So that cannot be the dominant channel. Now, what remains is basically core collapse supernovae or mechanisms that involve white dwarfs, which is related to type 1a supernovae. Now, even in those cases, we found that we still hope to detect FRBs in elliptical galaxies, but in our sample, we didn't. So that too can be sort of overruled as a dominant channel. So with this, we are left with the core collapse supernovae as the dominant channel that can produce most of the FRB sources. Now, this took me back to the discovery that we made back in 2020, where we found FRB-like emissions from our own Milky Way's magnetar, SGR 1935 plus 2154. So that observation actually sort of in line with the discovery or the evidence that we put on in this paper. Now, to sum up, I can clearly say that local universe FRBs are indeed very promising to understand the origins of fast radio bursts as evident from our work. Using the sample of 18 FRBs, as I said in the presentation, we concluded that core collapse supernovae are likely the dominant channel to produce FRBs. But I also want to say that in future, with more FRB localizations, which at least seems very likely, thanks to CHIME FRB oil trigger that expect basically to localize 100 FRBs, at least 100 FRBs every year to their host galaxies, that can actually make not just possible that we can test this hypothesis, but also check whether there are other channels, subdominant channels to produce FRBs. So in short, I can clearly say that FRBs does have a very bright future. Thank you for your attention.
Hello, everyone. Thank you for coming. I'm Alexander Kashlinsky. I represent a team of three of us who just published this paper in the Astrophysical Journal Letters yesterday. And it's a signal that we find in gamma ray sky, which to us is a total conundrum. It's very interesting, but the ultimate explanation is still to be given. And the signal that we find is the so-called dipole of the gamma ray background, diffuse gamma ray background. The most famous dipole, or in terms of backgrounds, is no doubt that of the cosmic microwave background, CMB. It has been known since 1970s. It represents a gold standard of measurements. It's measured with very high signal to noise, and its direction is known to better than 1 degree on the sky. And it's conventionally interpreted as being due to motion of the solar system and the galaxy at 370 kilometers per second in this particular direction, which results in the cosmic microwave background being about 0.1% hotter in one direction than in the opposite direction. So it's very important to understand the limitations of the conventional explanation of the cosmic microwave background. Most people by far assume that it's entirely due to our motion, in which case you just probe by Doppler shift the dipole in this background. But it could also have imprints if the dipole is not necessarily fully kinematic. Then it may probe the universe on very, very large scales the way it was prior to the inflationary expansion, way beyond the current horizon. So it's very important to establish if the entire CMB dipole is kinematic or there is another component. And this is what we intended to do in the gamma ray sky. We used Fermi Large Area Telescope data, 13 years of the data. And the reason we looked there at the GeV, giga electron volt energies, was because due to relativistic effects, the CMB, the dipole in the gamma ray sky should be about a factor of 5 greater than that in the CMB sky. So instead of 0.1% amplitude, we would be looking at a dipole of about 0.5 to 0.6% amplitude. That's the signal we intended to probe with a gamma ray sky with 13 years of data. So we took 13 years of Fermi-Lat observations, put it all together, removed the galaxy, removed the identified sources, removed other sources, including noise excursions, due to methodology which is now established from the cosmic infrared background work. And we found, to our surprise, a signal which was not 0.5 to 0.6%, but a different signal of much higher amplitude, highly statistically significant. And this is what we find there. Instead of 0.5 to 0.6%, the observed dipole of the diffuse gamma ray background at energies from about 3 to 100 giga electron volts is about a factor of 10 higher than what is expected from the CMB dipole. So that's the conundrum. So where can it come from? When we started this work, the other dipole that I will be talking about was not yet measured, but recently they found that there is a strong dipole of about the same amplitude, 6.5 to 7%, in the ultra high energy cosmic rays observed with Pierre Auger Observatory. And these are cosmic rays which are real monsters compared even to GeV photons. They're about 1 billion times more energetic than our gamma ray photons. And they have the dipole which is about 6.5 to 7% in roughly the same direction. So the two dipoles appear related to us. And it means that the gamma ray sky at GeV energies from about 3 to 100 GeV, or its dipole photons, dipolar photons, are related to these ultra high energy cosmic rays. And you can see the comparison of the two here. So it has about the same amplitude of about 6 to 7%. And then the two can be related by either ultra high energy cosmic rays cascading down and producing photons at GeV energies, or the two can be produced by the same sources independently. It turns out that the most obvious candidate, in fact, the only candidate of that would produce gamma rays at GeV energies from cascading is neutral pions that would be produced by various interactions of ultra high energy cosmic rays, and they almost immediately would decay into photons. However, the problem is energetic. You don't have enough energy here to produce what we observe in the gamma ray sky in the dipole from this cascading down of what are observed as ultra high energy cosmic rays. So then by elimination, what remains is a co-emission by as yet unknown sources of both ultra high energy cosmic rays and of the gamma ray photons, or perhaps yet another explanation that is yet to be proposed. And that's why we call this conundrum. This is who we are. Chris Schrader, who is in the audience, will be presenting technical details of this finding today at 3:20 in room 215. And if you have questions, you can contact, here are the email and the emails, and the cell phone. Email is preferred. Thank you very much.
Okay, good morning, everybody. I'm very excited to be here today on behalf of the South Pole Telescope collaboration to tell you about a recent result of ours, which investigates what triggers star formation in the most massive galaxies in the universe across billions of years. So one of the big questions astronomy is set out to answer is, how did we get here? More concretely, for those of us who work in the field of galaxy evolution, we want to know, how did we arrive at the galaxies that we see today? So galaxies come in all shapes and sizes, but if you look around in the nearby universe, you see that lots of galaxies will fall into one of these two categories, the galaxies that I picture here on this slide. So one of the main things that differentiates these two galaxies I'm showing you here is how much gas and star formation you have in these galaxies. So on the picture on the right, you have a lot of active star formation. There's a lot of gas fueling active star formation, and that's why you get these really nice blue colors, whereas the galaxies on the left are what we typically call red and dead galaxies. So how do galaxies then acquire this gas that's needed for star formation? Well, galaxies aren't closed boxes. They're constantly interacting with their environments through inflows and outflows with their atmospheres, which we call a circumgalactic medium. So it's really important to study this CGM to understand if you want to understand galaxy evolution. The problem is it's a bit difficult to study because it's very diffuse. And when you look at a galaxy cluster, like what I'm showing you here on the right, these galaxies eventually over time will start to share a lot of gas, and this gas gets hot enough that it glows in X-rays, which we can then observe with telescopes like Chandra. So this kind of acts as this fuel tank for the galaxies that are there in the center. But this fuel only fuels star formation when certain thermodynamic conditions are met. So for example, if you look at this quantity that I'm showing you here, this gas entropy, which is just telling you how much disorder there is in that gas. For galaxies that are embedded in these atmospheres that have really low central entropies, then these galaxies exhibit detectable levels of star formation. Galaxies that are in atmospheres that have high central entropies have not detectable levels of star formation. So this is this trigger for star forming material to condense out of the hot atmospheres. So clearly this is a very important process to forming stars in the most massive galaxies, but this has only really been shown until now in the most nearby systems. So we see here, this plot is for a look back time between 0 and 2 billion light years away. So we want to know, was atmospheric cooling just as important in the past as it is today? So as we go back in time, everything gets a lot more chaotic. The universe really had its foot on the gas pedal as you go towards about 10 billion years ago, and things like average star formation rate across all galaxies, the number of galaxies that are in mergers, black hole accretion, these are all peaking at around 10 billion years ago. So it's really important to study galaxies and the most massive galaxies at these distances because they can tell us a lot about how different processes could fuel star formation. But there's a lot of challenges to be able to study these really distant galaxies. So finding them in the first place is really difficult, especially in a non-biased way. And then following them all up to be able to connect this fuel tank to the ensuing star formation of these galaxies and how they grow is also difficult to obtain those data. So that's where our most recent paper comes in. This sample that's been about 10 years in the making. This we call this SBT Challenger sample. And this is an unbiased sample of 95 galaxy clusters that span about 10 billion years in evolution. So these are galaxy clusters based on the Sunyaev-Zel'dovich effect, some of the most distant galaxy clusters we've found. And for each of these galaxy clusters and their central galaxies, we have Challenger X-ray data amounting to about 1.5 months of total time and about 30 nights of optical spectroscopy to be able to connect that fuel tank to the ensuing star formation in these galaxies. So as I was showing you before, there's this trigger for making stars in the most massive galaxies, below which you don't get you get detectable levels of star formation and above which you don't. So this has only been shown in the most nearby systems, and we showed now for the first time that this trigger persists for about 10 billion years. So this you can see that there's this threshold that cleanly separates your detections from non-detections of star formation in these galaxies for about 10 billion years. The fact that it persists for so long implies a very strong, long-lived connection between cooling atmospheres and stars in your galaxies. On the flip side of this, so we mentioned that the cooling out of the atmosphere fuels star formation in your galaxies, but it also eventually fuels black hole accretion in the centers of those galaxies. And this eventually can lead to outflows, which we saw earlier, Kimberly talking about the active galactic nuclei. These outflows can suppress the amount of cooling that you're seeing. So this also regulates how much stars you can form in your galaxies. So this is visible in radio wavelengths, as I'm showing you here on the right. So as I said before, we have X-ray data to look at this fuel tank, this fuel supply in these galaxy clusters, in the galaxies. We could follow that down to optical wavelengths and see how many stars have formed. And then we could follow that down even further at radio wavelengths, where we have radio observations for all of our systems and see whether there's an actively accreting black hole in the centers of those galaxies. So just like the trigger for the star formation I showed you before, this trigger also exists for the same exact trigger in your atmospheres below the entropy, below which you get star formation. You also get black hole accretion in those same systems, and that's been shown for low nearby systems. But we also, and now we looking at the higher redshift systems or more distant systems, we show this dichotomy disappears. So this is a very different story than the star formation trigger that I showed you before. This is less well understood though, and so I think we'll have to wait for the next AAS press conference to be able to talk about this. But nonetheless, very exciting result. So just to summarize, we have this very unique sample of galaxy clusters that's been 10 years in the making. We have spanning 10 billion years of evolution. We have multi-wavelength data for all these systems to be able to connect fuel supply to what it fuels, its star formation and black hole feedback. And we see that the trigger for star formation in the largest galaxies persists out for 10 billion years. And we might be seeing the beginnings of black hole feedback, the hints of that. So if you want to see more info, more details, we can, I'll be talking later today at 2:20 in the Galaxy Clusters 2 session. And I have the paper here, the QR code for the preprint for that paper. So thank you all.
Great. Thank you so much, all of our speakers. So we're going to go ahead and move into the Q&A session now. So reminder, if you're in the room and have a question, when the mic comes to you, please identify yourself and your affiliation. And for those of you submitting questions online, same goes for you too.
Vincent Sutherland Planetariums, there we are live for Alex. So this will probably be a naive question, but most of us, I think, understand that the early gamma rays of the very early universe, as the universe cooled from the cosmic microwave background, all of those photons are highly redshifted into the microwave background radiation. Where do the expected gamma rays come from when you're looking at that gamma ray background? What's the source?
Assuming that this particular, you can hear me, right? Yeah. Assuming that this particular part of the gamma ray background is associated with the ultra high energy cosmic rays. The cosmic rays must be within a relatively nearby distance of about 100 megaparsecs or less, depending on whether they are protons or whether they're heavier particles. If they're heavier particles, the distance would be small. And this is because they would interact with the very abundant cosmic microwave background radiation photons, the so-called GZK effect. And then they would just cascade down. So this has to be a fairly recent phenomenon in the universe, about up to 100 megaparsec away. Where precisely, future work will tell. From what I understand, it's not inconceivable, and there were even proposals that the Euro-Ger ultra-high energy cosmic ray photons originate inside our own galaxy. But I think it's a minority view.
I'm Govert Schilling, freelance writer. From the Netherlands, also for Alexander. With a motion through space, I can understand you expect a dipole, which is sort of sinusoidal across the whole sky. But looking at your contour maps, it more looks like one particular source instead of a dipole. So how do I distinguish between the two?
Yeah, our dipole is not kinematic, it's for sure. It cannot be. If it were kinematic, the motion would be about 3,000 kilometers per second. It's highly unlikely, impossible in a way. So this dipole in ultra high energy cosmic rays, as well as in our diffuse gamma ray background, is in a way a source or a collection of sources. There is even there are some proposals of conglomeration of starburst galaxies and so on. So yes, they come from sources, but if it were purely kinematic, we would see a sinusoidal feature. We still see a sinusoidal feature, but that's what you saw across the whole sky. Yes, something is brighter than in the opposite direction, and it's what the map we present, as well as ultra high energy cosmic ray map. It's hard to see it because CMB dipole, it's measured with an exquisite accuracy, so-called signal to noise ratio exceeds 300. And when you translate it into directional uncertainties, the direction is known to within 0.1 degrees or so. So it's really a point on the sky. When other dipoles are measured, like ultra high energy cosmic rays or our diffuse gamma ray background, signal to noise that is achieved is about 4 to 6. It's highly statistically significant, but when you translate it into directional uncertainty, it's very large. It's about 20 degrees at 68% confidence level. So it's a huge area of the sky where there is exactly what is happening is hard to know. You need to measure it as exquisitely as CMB dipole. But we are continuing with this work. There is Fermi continuous observing, of course. We analyzed 13 years of data. This summer, 16 years will come online. So we will see what the future holds.
This is a question for Michael. Comes from Bill Waller of the Galactic Inquirer. Wants to know, how did you determine the gas entropy?
So the gas entropy it's a combination of density and temperature, which you can measure from the X-ray data.
Calla Cofield from JPL. This is for Aaron and Mohit. So the implication of your results, or, you know, the likely implication is that the formation process would somehow give these neutron stars the properties necessary to create an FRB. Is that correct? Or that it has some influence on that?
Hey, it seems to be just because, like, there are so many neutron stars in our own galaxy and magnetars, and those are not like FRBs. They're not producing FRBs which are as energetic as what we have seen in the case of extragalactic sources. It is possible that there is something intrinsic to the formation of those neutron stars, if we believe that FRBs are majorly neutron stars, that is causing them to produce FRBs at the rate that we're seeing from extragalactic sources. Yeah, so that's a mystery, but many authors actually think that that is the case.
I was just wondering if there's any other evidence of that, of formation processes influencing the properties of neutron stars.
For example, maybe Aaron can add it, but I can just give you one example and Aaron can give. Now, in the community of neutron stars, we have millisecond pulsars and we have normal pulsars. Now, millisecond pulsars, we know that they get the millisecond because of this binary motion. They energize when they take material from its companion, and then that's how the period becomes so small. But when you look at the isolated neutron stars, which are pulsars, of course, then in those cases, we don't see period as small as that. So that is like, even in our own case, we see that there is, two different classes. That's also possible in case of FRBs. That might answer your question, but Aaron, do you have anything else to add?
Yeah, I definitely agree with Mohit here. So the example that comes to mind is MSPs, millisecond pulsars. And there are other examples too. So neutron stars, very young neutron stars, there's some theories that predict very young millisecond magnetars that they should have some type of particular emission characteristics. And also very young pulsars like the Crab pulsar, they also have different emission characteristics. So definitely the formation channels, how they're formed, seems to have some influence on the type of emission that we see. Now, whether these particular types of examples that we just gave are related to FRBs, it's still a mystery. We're still really unraveling the phenomenon, but there are certainly, phenomenological similarities, I would say.
Yeah, so I was just going to follow up that it's probably too early for you to formulate ideas about why exactly the core collapse would lead to magnetars.
Sure. Can I add something? I think maybe the way I present it seems that, okay, we know everything about core collapse supernova, but that's also not true. There are like so many transients or time domain people who are still trying to understand why there are different types of light curves we see, what sort of stars can form. So that's again an unsolved mystery in that domain. So I think one big, personally, for if you ask me, thing is they're connecting two different domains now. One is radio astronomy and then core collapse. I think that way FRBs can not just be used as a probe or something about the cosmic baryons, but also can tell us the process that is involved in forming these cataclysmic sort of explosions, or the remnants of precisely cataclysmic explosions, which we still don't know. I think that new window that FRBs can open, I think it's exciting personally for me. Thank you. Amazing question.
I have a question for Kim, if I'm allowed to ask one. This is Carrie Hensley from the AAS. So you've shown us this really nice evidence for an AGN jet 5 million years ago with the accompanying burst of star formation. And I'm just curious, since we know that AGN do tend to turn off and on, is it possible to see evidence of like multiple epochs, or does one epoch kind of obliterate the evidence for previous epochs?
Thank you for that question. So I think we're just in the process of trying to understand how to look for multiple epochs. This signature has been predicted, but the reason that we're having trouble finding it, I think, is just because what you said, that the AGN turn off and on, and we don't quite know the cycle for that. And so in this case, we have one instance where we think we've seen the time scale. The other part of this problem is that this iron K alpha fluorescence nebula that we're seing could also be a reflection nebula, which might mean that there's a light travel time effect going on. And if that were true, then the AGN would have turned off 16,000 years ago, but we don't know. So I really think this is kind of opening up a new way to look for these things in the hard X-ray band. And I'm hoping we're going to be able to, find more of these signatures and maybe on different scales and answer the question you just asked. Can we map the time scales by looking at the different ridges, perhaps, of these features and galaxies nearby to us?
Very cool. Thank you.
Hi, Katie Mack, Perimeter Institute. My question is for Aaron and Mohit, about the FRBs. Is this study shedding any light on the difference between FRBs we see as repeaters and those we don't? How's that connected?
Very nice question. In fact, this is something that I've not discussed in my press release, but so just to give a background, there are FRBs. Most of the FRBs that we see, they do not repeat. Means we just see one burst, and despite of our efforts of following them up, we haven't seen any burst from them yet. But there are a small fraction of FRBs where we see them bursting, and in some even minute cases, we see them some sort of periodicity in the activity period. Now, it's definitely a natural question to ask. Okay, that the analysis that we have done, using that, can we say that somehow the formation channel for repeating FRBs are different from non-repeating FRBs? Now, we did compare repeating and non-repeating FRBs. We compared their host properties and all. And at least from that analysis, we found no strong evidence that suggests us that at least their local environment or the host galaxy in general are different. So that seems quite similar. And we definitely need more host associations. And I think Aaron knows better how we'll get those more host associations in next year or so. I think that will really answer this question that actually there exist two different population intrinsic formation channels to produce these sources. Yeah, thank you for this question.
I have another question. This one is for Alexander. Hi, this is Carrie Hensley from the AAS again. So if we put you in charge of the Gamma Ray Anisotropy Cosmic Conundrum Committee and gave you a bunch of money, unfortunately, I can't guarantee this. It's just a hypothetical. What kind of instruments would you want to build? What kind of data do you need to collect or models do you need to run that would advance our understanding of this problem?
Gosh, this is $1 million question. First of all, Fermi-Lat is alive and well and keeps observing. So this summer, there will be 16 years of integrations. When we started this project, there was even only 12 years of data. So we added 13 years when we got to final concrete results. I think it would be good we find signal, dipolar signal, which peaks, and this is tentatively, its signal to noise peaks between 5 to 30 GeV. So you would want to put your eggs in that energy basket, so to say. And it may be good to have a good energy resolution there. In terms of angular resolution, and of course you need all sky coverage for such signals. In terms of angular resolution, of Fermi-Lat is just fine in this regard at these energies. Would you agree, Chris? Yes. Yeah. But, if there is a lot of money, we can think further.
Great.
Are there any further questions in the room or online? Okay, then with that, let's go ahead and thank our speakers one more time. And thank you also to their public information officers and also to our sponsor, USRA. We will be back this afternoon for the final press conference, which I believe is Oddities in the Sky. I hope you'll all come and join us.